Okay. So it's really my pleasure, to have Yugo here, Yugo Takada. He has been doing some amazing work in quantum error correction recently. He's from Osaka University, Japan, and he has agreed to give a talk on improving threshold for fault-tolerant color code quantum computing by flagged weight optimization. So if you have any question or anything, please unmute and ask. And you go. The stage is all yours. Please, let us know what you did here. Yeah.
Okay, can I start? Can I start? Okay.
Yeah.
Okay. Thank you for your introduction. And thank you for inviting me today. I'm very glad to give a talk here. I'm Yugo Takada from Osaka University, Japan, and I'm now first year PhD student. Today I'm gonna talk about my recent paper that was recently published in PRS Quantum. The title of the paper is Improving Threshold for Fault-tolerant Color Code Quantum Computing by Flagged Weight Optimization. Okay, first I'm going to talk about the background of this research. In this talk, we will focus on color codes, which are promising quantum error correction code to build a fault-tolerant quantum computer. Color codes are topological codes defined on a three-colorable trivalent graph. There are two common types of two-dimensional color codes, like 488, or square octagonal color code, and 666, or hexagonal color code. In a color code, qubits are placed on vertices, and the stabilizer operators are defined on each face, like X-type stabilizers, and these stabilizers are symmetrically defined on each face. The advantage of color code is that we can implement the logical gate transversely, or we can implement all Clifford gates transversely, which means we can implement the logical gate to the encoded qubit by applying individual physical operation to every qubit in a code block. It can lead to low overhead quantum computation compared to surface code, because in surface code, some of Clifford gates, such as Hadamard gate and phase gate, cannot be implemented transversely. So it requires us to use some costly techniques. Despite the advantage, the color codes have some drawbacks. The one drawback is that decoding in color codes is more difficult than surface codes, because the decoding problem, like the structure of the decoding graph, is more complex than surface codes. And another drawback is that in quantum error correction, there is a value called threshold, below which we can decrease the logical error rate exponentially by increasing the number of physical qubits. It is known that the threshold of color codes is lower compared to surface code under the circuit level noise. Specifically, in the case of the square octagonal color code, the threshold is estimated to be around from 0.08% to 0.14%, depending on how we perform error correction. In the case of the hexagonal color code, the threshold is estimated to be around 0.2% to 0.47%, while in surface code, the value is around 1%, which is around one order of magnitude higher than that of color codes.
What?
So,
What's the intuition?
sorry?
So why is decoding difficult compared to surface code or the color code?
Decoding is difficult.
Yeah, you
Okay.
mentioned that the drawback is that decoding is difficult, right? So I mean, what is the intuition? Like, why is decoding difficult for color codes as compared to, let's say, surface codes?
Okay, thank you for the question. Because in the case of the surface code, okay, I have the picture of surface code. In the surface code, if one error occur, it flip only two stabilizers. Okay, so the decoding graph is just a graph, the normal graph, which means one edge connect to two vertices. So in this case, we can use the well-known efficient classical algorithm such as minimum weight perfect matching, which is efficient. But in the case of a color code, the physical qubit connect to like three stabilizers. So one error flip three stabilizers. So the decoding graph is hypergraph, which is more complex. So we cannot straightforwardly use the efficient classical algorithms such as minimum weight perfect matching. So this is the reason. Okay.
Yeah, please continue.
Okay. Thank you. Yeah, the focus of this study is to improve the threshold of color codes. Okay, let me explain why the threshold of color codes under circuit level noise are low to begin with. In fact, under the code capacity noise or phenomenological noise, in which only data errors or data errors and measurement errors occur independently, the threshold of color codes on surface code are not that different, but the situation is different in the case of the circuit level noise. The circuit level noise is a noise model where every operation in a quantum circuit can suffer from errors. Like this is a quantum circuit under the circuit level noise. Every operation, including the state preparation and quantum gates and measurement, and also idling operation, can suffer from errors. In the conventional syndrome measurement circuits, in which we perform indirect measurement by using a single answer qubit and apply some CNOT gates and measure the answer qubit at the end of the circuit. In this circuit, the color codes are more susceptible to errors because of the high weight stabilizers. Like in the case of the surface codes, the stabilizer generators are defined as the weightful Z-type Pauli operators and weightful X-type Pauli operators. But in the case of the color codes, the stabilizers are defined as at most weight 6 or weight 8 stabilizers, depending on which color codes we are considering. Because of that, the depth of the syndrome measurement circuit in color codes are higher compared to surface code. So there are many error locations, and errors can propagate more. These are the reasons why the threshold of color codes under circuit level noise are low. In more detail about the conventional syndrome measurement circuits, these are
So, but there has been this thing called, flocate color code, right? I mean, I think recently there was some paper they were the flocatified color code. So in flocate color code, the weight of the stabilizers you can reduce, right? You can bring it to weight 2, for example.
yeah. Yeah, I
So,
know in the case of in the like Flocky code, we can measure the stabilizer by only measuring the two body like checks. Yeah. So sorry,
Yeah,
what?
because I mean, what I'm saying that, like, I mean, obviously, maybe you are following a complementary approach, but maybe you can comment about it now or later. That so basically, like the large weight of the stabilizers is a problem. Like, for example, for color code, as you rightly mentioned, and one would like to reduce the weight of the stabilizers. Now, obviously, one can use different weight reduction techniques. One of the common weight reduction technique that people use, let's say recently popular, is this thing called flocketification. So you can start with like some code, and you can flocketify it, and the flocketified version will have a smaller weight check operators. So for example, people have, like using ZX calculus, people have managed to, I think there was some paper by some people from, I think, Berlin, like they managed to flocketify the color code. So like maybe I mean maybe now or later whenever you are talking about, I think it would be nice to see like how your work compares, like let's say like the weight that you have, and I mean, in case you want to comment about that.
Oh, okay. Thank you. Um, yeah. So I will continue. These are the X stabilizer measurement circuits. The stabilizer measurement circuits are similar, except that the basis change to the basis and the direction of the CNOT gate is reversed. It requires applying a number of CNOT steps equal to the number of the weight of the stabilizers. Yeah. So in the case of the scale octane color code, we need to implement 8 steps of the CNOT gates and 6 steps in the case of the hexagonal color codes. For those who are not familiar with decoding, I'm going to briefly explain what is decoding in color codes. Because color codes are CSS code, which means stabilizers consist of either only power X or power Z, we can decode X errors and Z errors separately if we don't consider the correlation. For example, if errors occur like this, the syndrome of the stabilizers that anti-commit with error change to -1, so the blue one and red one change to -1, and green one doesn't change because it commit with errors. Decoding is a classical process of estimating the actual errors from the syndrome we get. We can find most likely errors by finding a set of errors having minimum weight given a syndrome using some classical algorithm. This is decoding under the code capacity noise. Like, the phenomenological noise is a noise model where measurement errors also occur in addition to the data errors. And probabilities of each data and measurement errors are independent and identically distributed. And in the presence of measurement errors, we need to repeat syndrome measurement a number of times to treat measurement errors. On other decoder, here we consider the integer programming decoder for its simplicity to see how it is formulated. In this decoder, given a syndrome, we minimize the total number of data errors and measurement errors by using binary variables S, X, and R. Here, F is a phase, and V represents a vertex. The constraint of the integer programming problem is that errors and syndrome should be consistent, and because the difference of the syndrome between time step t and t-1 indicates the data errors that have occurred in time step t. So the difference between t and t-1 becomes the constraint by also taking into account the measurement errors in time step t and t-1. And the cost function is the total sum of data errors and measurement errors across all time steps. Okay. In the case of the circuit level noise, the probabilities of resulting in data and measurement errors occurring are not identical because there are correlated errors on the way errors occur and propagate differs for each qubit. So setting a weight of a decoder, which is one of the parameter in decoder, for each error lead to improved performance. In the conventional way of setting a weight, the weight is defined based on error probability distribution. The weight is the coefficient of the variable corresponding to log data and measurement errors, and it is defined as minus log of p over 1 minus p, where p is error probabilities. The meaning of this weight is that the higher the probability is, the smaller the weight becomes. So the errors with high probabilities is more likely to be estimated in the decoding algorithm. But the conventional weight is not optimized in the sense that it fails to account for the impact of correlated errors unless we add some additional variable corresponding to correlated errors, such as Foucault errors. Okay, from here, let's move on to the proposed method. In short, in the syndrome measurements, we use a gadget named flag gadget for each phase instead of using one single answer qubit. Then we use flag information for weight optimization to decode more accurately. Here we use two types of gadget named 4-qubit flag gadget and 2-qubit flag gadget. These gadgets are circuits that can flag certain types of errors from the measurement outcome and at the same time provides syndrome by first preparing cat state, then interacting with data qubit in the select line, and finally performing post-processing and measurement. Okay, to be specific about each part of this gadget, cat states reduce the number of synth steps to data qubits, resulting in a reduction in idle noise. Additionally, the decrease in error propagation path leads to a reduction in error propagation. Regarding the flag, for example, if XL occurs here in a 4-qubit flag gadget and propagates in this way, it is detected by the fact that 3 flags are triggered. Such information about propagated errors allows us to correct errors more accurately. In detail about the syndrome measurement circuit of my proposed method, in the case of the square octagonal color codes, the 4-qubit flag gadget are used at the octagonal faces, and 2-qubit flag gadgets are used at the square and trapezoidal faces, where CNOT gates are applied to the 2 neighboring data qubits from each answer qubit. In the case of the hexagonal color codes, 2-qubit flag gadgets are used at each phase, where CNOT gates are applied to the 3 neighboring data qubits from each answer qubit for the hexagonal phases, and applied to the 2 neighboring data qubits in the case of the trapezoidal phases. In both cases, the number of synth steps has been reduced to 3 steps, which is minimum in the case of the color codes, because in color codes, up to 3 stabilizer generators are involved for data qubit, and at each time, at most 1 operation can be applied to any given qubit. Then I will explain how to use the flag information for weight optimization, which is the main part of my proposed method. We here call flag weight optimization, FWO. In this work, we set the weight of a decoder using conditional error probabilities conditioned on flag values. In the case of the X error correction, for weight of data errors, we use the conditional error probabilities conditioned on the old flag values in the measurement of the X stabilizers acting on the corresponding data qubits at the same time step. The meaning is that the conditional error probabilities when some flags are triggered is higher compared to when no flags are triggered. Like also for weight of the measurement errors, we use conditional error probabilities conditioned on the flag values in the measurement of the D stabilizers that measures the corresponding syndrome. This way of setting weights allows us to decode more accurately than conventional one because we can take into account some correlated errors that trigger the flag qubits, the measurement of the flag qubits. Okay, the conditional error probabilities we have discussed so far actually needs to be estimated in advance. In our study, we propose a method to estimate them in a way that is efficient, accurate, and can be used when the underlying noise is unknown. We estimate the conditional error probabilities by repeatedly execute a tailored quantum circuit offline prior to the decoding. Then we obtain the information about errors from the measurement outcome of the circuit. The conditional error probabilities estimated at a single time step are used for all time steps because syndrome measurements are periodic. This is a tailored quantum circuit tailored for estimating the conditional error probabilities that is used when defining the weight of X errors, X error correction decoder with a distance-free color code. In a one-cycle syndrome measurement circuit where X stabilizer measurement is performed, followed by Z stabilizer measurement, we initialize the data qubit to the tensor product of zero state instead of cold state and initialize all answer qubit for X stabilizer measurement to zero state. Then we detect data deterministically through direct transversal measurement of the data qubits. This circuit enables us to detect errors occurring in a qubit solely based on the outcome of a single qubit measurement for that qubit. So I estimate the conditional error probabilities used in the weight that we propose in this way. In addition to the flagged weight optimization method, we also perform other procedure using flag information to further improve the performance, which is called deflagging procedure. This is a part of the syndrome measurement circuit. When some errors occur, like this, and flags are triggered during the syndrome measurement, we apply a proper recovery operation at this point, or update power flame, because we know that if this error occurs and the propagated errors are these like two X operators. The same procedure is also performed when estimating the conditional error probabilities. This procedure enables us to correct some errors that cannot be corrected by the decoding or using only the flagged weight optimization that I propose. Okay, these are the proposed method. Then I will move on to the numerical simulation. This is the result for the square octagonal color codes. Dotted line is a result of the proposed method, and solid line is a result of the proposed method, and dotted line is a result of the single answer method, like conventional way of extracting syndrome. Horizontal line is the physical error rate, and vertical line is the logical error rate. The threshold we obtained is around 0.27%, while the threshold for the single answer method is 0.15%. So our method achieves the threshold weight that is around 1.8 times higher than the conventional method. This value also surpassed all previous studies. Also, the logical error rates in the low error rate regimes were improved by almost 1 order of magnitude compared to the single answer method. This is a result of the hexagonal color code. Again, the solid line is a proposed method, and dotted line is a single answer method. The threshold we obtain is around 0.36%, which is around 1.3 times higher than that of the single answer method. And this threshold is almost same as the highest value among the previous study that employs the same noise model. And in our method, the logical GAR rate is slightly lower than that of X stabilizer, X logical X error rate, because the schedule of the syndrome measurement we use is like first we perform all X stabilizer and then perform G stabilizer. So in the initial time step, we cannot use the flag information for the X errors. Yeah, and similar to the previous case, the logical error rates were improved by almost 1 order of magnitude in the low error regimes in the case of the hexagonal color codes. Okay. In the previous two slides, I showed the result obtained by combined contributions of several techniques, such as the use of cat states and FWO and deflagging. But we were not sure how much FWO itself improves performance, and we want to know it because the FWO is the main proposal of this paper. So I show the numerical result that is achieved by using cap state and deflagging and FWO, and the one that use cat state and deflagging but without FWO. So by comparing these two results, we can see how much FWO itself improves the performance. And you can see that the method with FWO achieves the threshold around 0.27%, but if we don't use FWO, it achieves threshold only around 0.18%. So it means the FWO significantly contributes to the improvement of the threshold. Okay. In conclusion, So we propose a method to improve the circuit level threshold of color codes by flagged weight optimization. Our result for the square octagon color codes surpassed the threshold of all previous studies. And our result for the hexagonal color code is also comparable to the best known value. And in this study, we used integer programming decoder to just compare the result between my proposed method and the conventional method. But it doesn't mean we cannot use other decoder. So our method can also be applied to other weight-based decoders. Another possible future work is that is to apply our techniques to wider classes of QEC codes, such as high-rate quantum LDPC codes, because the high-rate quantum LDPC codes sometimes have high-weight stabilizer generators. So I believe that my method can be used in this case. Okay, maybe a little bit early than the expected time, but this is end of talk. If you have question, please feel free to ask.
Okay. Yeah, this was very pedagogical. I mean, this flag bit optimization technique sounds good. I mean, one can, I think, apply to, I don't know, some of these recent LDPC codes, right? I mean, they have like weight 6 and higher, and also I think this quantum radial codes, they have also like high weight and so on.
Yeah.
So definitely quite I think promising approach.
Yeah.
I
Can I
see.
ask
You know,
something?
I just, yeah, Toby, please ask here.
I mean, you can.
Please continue.
Oh, yeah. So yeah, thank you very much, Doug. But we met in Osaka, if you remember. Sorry, you work there. So yeah, it's great to see it.
Great.
I'm just asking. Basically, this was just exactly what Keisha was asking. How do you find this flagging? Like, what did you use some kind of systematic procedure, or you just try and error? Like, how do you systematically find these kind of correct states? Like, do you need to use this cat style or some other state, right? Or how do you arrange your cat qubits, and how do you arrange your schedule of doing syndrome measurements? How do you define that? Is it like try and error, or is there like a systematic approach how you can do this?
Okay, thank you for the question. Basically, I basically I didn't consider any like systematic way. I just by like handmade, I made circuits to like optimize. So actually, I tried many ways of many example of circuit, and I found a circuit that achieves the least like low-child error rate, but I didn't verify that it is optimal. But I believe that it's like near.
But how do you check this numerically, or
Sorry,
like how do you check this?
did
Like you write down a circuit and then you basically you get the threshold, or how do you figure out if it's good or not?
Yeah, I did numeric estimation for many examples.
But is there a way to guess at least that this is a good solution or this is a bad solution? Like,
sorry.
Is there like a way to guess at least? Like, let's say maybe just do some kind of stabilizer simulation and check how the X and Z's propagate. You can
No,
check the flex.
I calculated the logical error rate.
Okay, so you have to always check the error rate. And how do you get the correct flag? How do you know which is the flag qubit?
Sorry, I don't get the point.
Like you mean to assign the flag qubits, right? And say like what to do. Yeah, how do you choose that?
Flag qubits? So you mean
how do you assign the flag qubits?
I mean there are like many ways to. So there are many flag gadgets that we can choose. So do you mean that why I choose this flag circuit.
Yeah. How do you select them? It's like a library of them or somewhere?
Library? No, so the one meaning is that I wanted to, the one thing I need to do is that to reduce the depth of the circuit. So in that sense, by using 4-qubit flag gadget in the scale color code, we can achieve depth 3, zero depth. So,
but you already knew about the flag gadget before, like this is already published before. Someone already came up with this flag gadget beforehand?
Yeah.
I see. Yeah.
Yeah, so
So-
this 4-qubit flag gadget came up with like someone previously.
I see.
So,
No,
but
why I'm asking this is very busy. I mean, this is basically a question Keisha asked, right? Nowadays there's so many codes, right? There's not just the color code and the surface code, but there's like the private bicycle codes and the radial codes and whatever code, right? I mean, there's so many kinds, circuit codes. That would be nice to have a systematic way of basically having these kind of flag gadgets and how to make these.
Actually,
The correct way of doing is how to
there
compress the syndrome measure. Like if
I don't-
the systematic way of doing this now for all possible codes, maybe some framework or something that would be nice to have.
I don't know how these things compare with, there is 3-step process by 3-step or three approach process by, by Hastings. So Hastings has this weight reduction technique. And I don't know how does so there are different approaches. So there is one, this one there is one can try, like Hastings approach. Then on top of that, there is flocketification. In fact, for color code, like there are, using ZX calculus, people developed, the paper name title is flocketifying color code via ZX calculus. So any place where, let's say the weight of the operator is like large, like large weight operators lead to, like many kinds of error, hook errors and so on. And one always wants to reduce it. So let's say if you can systematize it, that would be very nice, because then it becomes just like a compiler. You try it to another code and you can reduce, the weight, and it can help you in terms of threshold and so on.
Yeah, I agree that if we can have a systematic way to construct circuit, it will be very nice. Yeah, I will consider about it.
Hey, so I'm just wondering, if you have thought about, or if there's like an existing result that uses this flagging method to decoding for subsystem codes, because I imagine it will be quite different. Because in subsystem codes, like you obtain your error syndromes by measuring the gauge generators. So yeah, I'm just wondering if there's such thing like flagged subsystem code decoding.
Yeah, so are you talking about the paper by Chris Chamber or something?
No, I'm not. Yeah, I'm not referring to any paper. I'm just wondering if you have thought of this, or if you know any existing result, for this flagging method for subsystem codes.
Subsystem codes.
Yeah.
Okay, not subsystem code, but I know one paper by Chris Chamberlain that use flag information for decoding graph as well, but it's different from my way of using flag information. But in his paper, the threshold in the hexagonal color code was 0.2%, which is lower than my method.
Okay. But did they use it on a subsystem code, or?
No, just the hexagonal color code.
Okay, I see.
like for subsystem code, I know one paper by also like maybe Chris Chamberlain that use kind of hexagonal code or something in like PRX, if I remember correctly. In this paper, the flag is used for subsystem code, but I don't remember exactly the result of that paper.
Okay, yeah, that's fine. Do you remember what's the title of the paper by any chance,
By
or like the authors?
which paper?
The flagging for subsystem code that you mentioned just now.
Maybe Chris Chamberlain. Okay.
So Andrew, are you thinking like there is color code, right? And then one can think of subsystem color code where one can further reduce the weight, and
Yeah.
then maybe you can flag it further, and so that, yeah, I think that will be nice. Exactly.
Because in subsystem codes, you have lower weight measurements, right? Like, although you need to do more measurements, I'm just, curious if that could improve this further the flagging method.
Yeah, it sounds interesting. I found the paper that I mentioned. The title is Topological and Subsystem Codes on Low Degree Graphs with Flag Qubits.
Awesome. Thanks very much.
In 2020.
Thanks.
Yeah, thank you.
Are there other questions for you?
Maybe a question maybe that I always want to ask, like, which color code is better, the 4.88 or the 666? Or what's the difference between them? I always wondered that. Like, why would you choose one or the other?
I think the 666 is better. Like until a few years or like 10 years ago, people were considering that in 6.6 color code, we cannot implement phase gate transversely. People were thinking that. But by Alexander Kubiker's paper, it was shown that even in like hexagonal color code, we can implement phase gate transversely by applying S gate to some qubits and applying S dagger to some qubits, which is also transversal in some sense. So before this paper came out, people were thinking that 488 is practical in terms of a transversality of the gate. But now we know that all clipboard gates can be implemented transversally, even in the hexagonal color code. And hexagonal color codes has high thresholds and low weight stabilizers. So I think there is like almost no way to use 488 color code if there is no specific reason.
Okay, so it's mostly historic reasons.
Yeah.
Interesting.
So, like in the recent papers about color codes, most of the researchers consider hexagonal color codes. Maybe, yeah.
Interesting. Yeah. Maybe one more question was one because so you said that decoding is difficult, right? Because it's basically a hypergraph, right? If you write on the Tanner graph, it's a hypergraph, so you can't just use graph decoding as normal. Therefore, the decoding is harder. But let's say you will find, for example, if you compare to the birated bicycle by IBM that they recently proposed, that also is a hypergraph.
Yeah.
But they basically use BPOST, like a belief propagation with ordered post-processing, and it works very well.
Yeah.
But if you use the same method that IBM used and apply to the color code, you find it behaves very badly. Like you get a very bad threshold. So I'm wondering, why is that? Like, is there a fundamental difference between, let's say, the 6-zip code and the bicycle by IBM? Although they're both, let's say, they have the similar graphs, you would think, like they are like hypergraphs. One seems to be easier than the other. Like the color code seems to be way harder than the from IBM. Is there some fundamental reason to it, or have you observed something like this?
Actually, I'm not so familiar with like BPOST or something like that, so I don't know the intuition about that. But at least in color codes, I mentioned that the decoding is difficult. But recently, in these few years, many like decoder for color codes are have been proposed. So in these decoders, mostly people consider the way that by like reducing the decoding problem of color code to like surface code, by decomposing the problem decoding problem, we can use minimum weight packet matching.
Yes. Yeah, maybe decoder or something.
So, and I know many decoder, like also Craig Gidney, he wrote a paper about what is called the open source decoder, color code decoder, Chromobis.
Oh yeah, Chromobis. Yes.
Which is based on the Mobius decoder.
Yes.
And in this decoder also we can use minimum weight packet matching somehow, so it is efficient. And also recently, like Hue Wu, he is in like Yale University, proposed minimum weight parity factor decoder, which is decoder for hypergraph, and it is the average complexity of this decoder is almost linear time, he claimed. So I think the decoding for color codes is no longer a big problem, I think, recently.
Okay, thanks.
Okay, maybe you could, like also share your slides and I will share with people in the Discord. If you want, you can also join the Discord channel. I think, yeah, seems there are no more questions. If there are any question, please ask, maybe one more question. Or if not, like maybe let's thank you for a very pedagogical talk and like, in leading it, so many nice discussions we had. Next week we will have a talk by Jahak Lee, and we are currently in the audience also. And yeah, so that's it. See you guys next week.
Thank you for listening.
Yeah, thank you.
Thanks. See ya.
Thank you. Bye.
We'll see you.